Alright, welcome back. We are in the next part of the lecture here, the third part, and we're going to start talking in more detail about this idea about what happens when radiation actually hits an object. And again, we're going to talk about this in all kinds of examples in your day-to-day life, but we're also going to focus on in the context of atmospheric sciences. What actually happens when energy that you've seen, emitted by something, the sun, the surface of the earth, a cloud, whatever, what happens when it hits a cloud, an ozone molecule, the surface of the ocean, whatever. And there are basically four things that can happen when a photon of radiation or a wave of radiation hits an object. And you can remember them with the abbreviation ARTS, A-R-T-S. Now, one is absorbed, then reflected, or transmitted, or scattered. Let's actually talk about each of these in some detail here. Now, we've already talked about absorbed. An object, when it absorbs radiation, what that means is that when the photon of radiation or the wavelength of radiation hit the object, that stopped the radiation, and the energy in the radiation was used to increase the temperature of the object that did the absorbing. That's how a microwave oven worked, as you might recall. The magnetron gave off microwave radiation that the food was very good at. In particular, the water molecules in the food are very good at absorbing, and then that increases the temperature of the water molecules in the food or whatever. We saw an example of that with regard to like a hot parking lot where the sun was shining on the parking lot. The parking lot was absorbing the radiation and increasing the temperature of the surface of the asphalt or whatever. If we were going to be thinking about that in the context of the atmosphere, well, in the atmosphere, ozone absorbs ultraviolet radiation. Ozone, you remember, is a type of oxygen. It's a form of oxygen, O3, that happens to be spectacularly good at absorbing radiation that has a wavelength that we call ultraviolet radiation. It's a type of shortwave radiation from the sun, and ozone is just really, there aren't really all that many ozone molecules in the atmosphere, but they're really, really good at absorbing ultraviolet radiation, which increases their temperature. That's part of the reason why temperature increases with respect to height in the stratosphere. Greenhouse gases in the Earth's atmosphere, carbon dioxide, methane, and so on, are very good at absorbing infrared radiation. The kind of radiation that the surface of the Earth and so on emits is a type of long-wave radiation that the Earth's surface is emitting and should be heading out as energy and heat lost out to space, but greenhouse gases in the Earth's atmosphere are very good at absorbing that radiation, which increases their temperature. Oh, okay. The surface of the Earth absorbs all that shortwave radiation from the sun, which is very good at increasing the temperature of the surface of the Earth. That's why it gets hot during the day at the surface of the Earth, because when the sun is shining on the ground warms up. Okay? Absorbing is not so hard to think about. ARTS. The next one is reflection. Reflection is about when a photon of radiation hits an object and then gets sent back, reflects off of the object, and gets sent back basically in the direction from which it came. It doesn't have to be exactly the direction it came, but more or less back where it came from. A mirror obviously reflects the kind of radiation that we call visible light. Mirrors don't necessarily reflect radio waves, mirrors don't necessarily reflect infrared radiation, but they do reflect the molecules of silver and so on the backside of the mirror reflect visible light. Reflecting radiation does not change the temperature of the object doing the reflection, nor does it stop the radiation. The radiation just turns around and goes the other direction. Okay? Snow. Snow reflects visible light very well. Snow, when the ground is covered with snow and sunlight shines on it, most of the sunlight reflects off the surface of the snow and heads back up into the sky without warming the snow up. Reflection doesn't warm the snow. In fact, once the ground is covered with snow, it's hard to warm the ground back up because most of the sunlight is reflecting off the surface. That's an important part of the role of clouds in the Earth's atmosphere because clouds reflect shortwave radiation before it gets to the surface of the Earth. Sunlight comes through 90-some million miles of space, hits the top of the clouds, and reflects back up into space without ever changing the temperature of the cloud, the ground, the air, anything. Oh, okay. Snowpack reflects a lot of shortwave radiation. Raindrops reflect radar radiation, which is a type of microwave radiation. We're going to learn about that. I think it's the 6th module of the course when we learn quite a bit more about how radar systems work. But the radar dish at the radar station emits microwave radiation, reflects that radiation off of raindrops in the cloud, and then that radiation comes back to the station where equipment measures it. Lots of examples of what reflection does in the Earth's atmosphere. Now, there's actually a key vocabulary word associated with reflection, and that's albedo. Albedo is a property of objects that describes how good they are at reflecting. in particular, how good they are at reflecting visible radiation, like light. Okay, so an albedo is a number between 0 and 1. 1 means it reflects all the light that hits it, and 0 means it reflects none of the light that hits it. So like a black object has a very low albedo, and a white object, or a mirror or something that reflects most of the light that hits it, has a very high albedo. And I put a little chart in here just to give you a sense here. So something like snow, or like a very white type of rock, let's say granite and so on, have a very high albedo, 0.8, 0.9. They're reflecting most of the radiation that hits them, whereas things like dark rock surfaces from lava, like basalt, and a forest and so on, or a parking lot, have a very low albedo. They are reflecting very little of the radiation that hits them. They are absorbing most of the radiation. Albedo is an important property of a surface. We want to know how much radiation it's reflecting away, but it specifically refers to shortwave radiation in the form of light. Okay, we don't worry about the albedo of something for infrared radiation or something like that. ARTS, the T is transmission, or transmitted. Now this is an important vocabulary word here because people tend to use the word wrong. When we mean transmit here, we mean that the radiation passes through an object. Sunlight mostly is transmitted through the Earth's atmosphere. It passes right through it. And when the radiation passes through an object without being stopped or reflected or anything like that, it does not change the temperature of the object. By and large, visible light is transmitted through the Earth's atmosphere. That's why we can see, right? If I can look up and see the sun, apparently light from the sun is making it through the atmosphere to my eye. It is being transmitted. The atmosphere, for example, mostly transmits radio waves, another type of radiation, right? That's why the radiation from your cell phone is able to make it to the tower, right? The radiation mostly is being transmitted. It's not being absorbed by the atmosphere or so on. For that matter, like in the picture there, all those people using their phones indoors, right? By and large, the radio waves that are being created by the cell phone antenna transmit through the walls, okay? An X-ray. When you get your X-rays taken at the dental office there, most of the radiation passes right through, is transmitted through your the soft tissues, and it is mostly absorbed by the hard tissues, like the dentin and so on in your teeth and so on. And so they can use that information then when it exposes the film on the radiation on the X-ray. It could be used to make a picture of your teeth. Transmitting radiation does not change the temperature of the object that the radiation passed through, and it does not stop the radiation. Now in the atmosphere, of course, we talked about the fact that the atmosphere is pretty good at transmitting visible radiation. The atmosphere is pretty good at transmitting radio waves. Just to draw another example to radar, when we learn more about radar, radar cannot see cloud droplets because cloud droplets, the tiny little drops that make up a cloud, that are smaller than the naked eye can see, transmit the microwave radar radiation, and as a consequence the radiation just goes right through those droplets rather than reflecting off of them like it does off the raindrops. Okay. ARTS. We have one other thing apparently that can happen when radiation hits an object, and that is scattered. Now scattered is actually very, very similar to reflected. In fact, some textbooks would put these two things together, but from the point of view of meteorology, there's actually kind of a difference. When radiation hits an object and is scattered by that object, that means it is kind of like it's reflected, but it's sent off in a new direction. It didn't go back in the direction from which it came, like when you reflect radiation. It can go, in a new direction, not necessarily back. But otherwise, other than that, it's very similar. And just like reflection, scattering doesn't stop the radiation, it just sends it off in a new direction. And just like reflection, scattering doesn't change the temperature of the object doing the scattering. So, in a lot of ways, it is a lot like reflection. In practice, in terms of the actual properties going on in the atoms, it's quite different. But it's a very similar process. And scattering turns out to be very important for lots of the properties and things that you're interested in an atmospheric science class. Scattering turns out to be why the sky is blue. Scattering turns out to be why the sky is red at sunset. Scattering is why it's hard to see through fog, and so on. Now, some of those things we're going to learn more about through the readings or through handouts and so on. I do want to spend a few little minutes, though, real quick, just as an example, using how scattering explains why the sky is blue. Alright, now, over there on the right side here, see I've got those little two guys sitting there on the ground and they're looking up at the sun. And you might notice the sky is black in this picture here. If there were no air molecules in the sky, you would look up and the sky would be black every which way, except in the direction of the sun. If you looked in the direction of the sun, please don't look in the direction of the sun. If you looked in the direction of the sun, though, you'd see a whole bunch of light. We know this because, like, for example, we've been to the moon. At the moon, even during the day, the sky is black except where the sun is. Without air molecules, there would be no photons coming down from the sun and hitting either eye in different directions. Let's explain here. By and large, let's put the atmosphere in here. By and large, the atmosphere transmits radiation for the sun, shortwave radiation. Different colors of light are, in fact, caused by slightly different wavelengths of those photons of light that are coming from the sun there. So the only difference really between green and yellow and orange and red and all the colors of the rainbow is they have slightly different wavelengths of the radiation. And if we actually looked up at the sun, we would see that the radiation coming from the sun through all the atmosphere contains photons of green and indigo and yellow and all the colors of the rainbow except blue. So if I had some instrument and I could point it up at the sun, I'd see all these photons of all these different colors of light, but not blue. As it happens, the molecules that make up Earth's atmosphere, things like oxygen and nitrogen, tend to be really good at transmitting photons of visible radiation, except blue, they're very good at scattering. It just has to do with exactly the size of those molecules and so on. So when a photon of blue light hits the top of the Earth's atmosphere and starts hitting these molecules of oxygen and nitrogen and so on, it starts getting scattered, sent off in a new direction. Picture like a pinball machine or something like that. It's just bouncing around, hitting, the ball just keeps hitting all those little flippers and all the little bouncers and so on. And in the same way, the photon of blue light is just bouncing around off oxygen and nitrogen and all these different molecules in the Earth's atmosphere. Bouncing and bouncing and bouncing in every different direction. Not passing through the atmosphere in a straight line, like the green and the red and the orange and so on do. And as a consequence, from the point of view of those two little dudes sitting there on the ground, the blue photons are coming from pretty much every direction, right? They're all really coming from the sun, but the last hit of a molecule before they go into their eye is in a direction other than the sun. So when they look in that direction, or that direction, or that direction, they see blue photons. The sky looks blue to them. You're not seeing the sky, though. You're seeing the sun. It's just that the photons of light from the sun took a very crazy path to get there. Now, to illustrate this a little bit better, let me just show you. I love to make comparisons to Plinko on The Price is Right. Hopefully you've seen The Price is Right, and you know this little game here that I'm talking about here. People who've taken other classes with me know I love to find analogies with Plinko. But let's make an example of Plinko here. Remember this game here? You drop this little chip into the game board here, and it bounces around off all these nails along the way and falls into a slot down there at the bottom. Alright, well, let's think about those little chips that we're dropping there as photons. They are photons of light from the sun. And let's put a little dude down here in the $5,000 spot. Okay, any photon that lands in, any chip that lands in that spot there is like a photon that he saw. Well, you know as well as I do that when they drop the chip down there at the top of the Plinko board, it bounces and comes from every which way. The actual photons that make it down to that guy down there come from any different direction. They're not going to come from just straight above him. So any blue photon that has been bouncing around in the Earth's atmosphere all the way as it moves through the Earth's atmosphere, that last little hop it makes before it goes into the guy's eye, or that last little hop the Plinko chip makes before it goes into the $5,000 spot at the bottom there, will be coming from any given direction, not anything to do with where the guy up above dropped it. So from his point of view, the winning chips come from lots of directions. In contrast, just to kind of make it a little more clear, let's say you could also play by, instead of dropping a Plinko chip, you could drop a big heavy bowling ball down the Plinko board that could just break all the little pegs along the way. Think of that as being all the other colors of the rainbow, yellow and orange and red and so on. They just plow through the Earth's atmosphere without actually interacting with oxygen and nitrogen and so on. They all come straight through the Earth's atmosphere without bouncing off all those molecules. Only the blue, so all the colors of light except blue come straight through the Earth's atmosphere, but the blue molecules have bounced around so many different ways. By the time they get to your eye, they're coming from any direction, not necessarily the direction of the sun. You can use this actually as a way of understanding, like anytime you have trouble seeing, like on a foggy night. Okay, here's a little guy hanging out down there on the road on a foggy night, and there's a tow truck coming his way. And the tow truck's lights are giving off photons of light, And much of the light is headed in the direction of, we're only worried about the light that actually heads towards his eye, right? I mean, it's actually giving off radiation in lots of directions. The problem is, of course, the fog along the way is, well, it's also the fog droplets along the way are scattering some of those photons of light. And so by the time the light gets to that guy's eye, it's not so bright anymore, because lots of the photons have been lost by scattering. They have scattered off into new directions away from his eye, and they're lost. We'll never see those photons. So the beam has been getting dimmer and dimmer because the droplets of fog between the man and the headlights are scattering some of those photons of radiation away. On the other hand, well, sometimes when just by dumb luck, some of those photons of radiation that got scattered off in a new direction do get scattered again and happen by just dumb luck to get scattered in the direction of his eye. So if you look at those diagrams down there, you can actually see some examples where a photon of radiation is being scattered towards the guy's eye. So he sees photons of light that come from the headlights, and they're not coming from the direction of the headlights. They're in new directions. That's why, from the man's point of view, there's actually photons of light coming from kind of a wide area. Yeah, a lot of the light coming right from the direction of the headlights itself, but actually, he's seeing kind of a glow of headlight lights all over here. Well, of course he is. Those are photons of light from the headlights that got scattered into the direction of his eye. That doesn't mean that the car is that way. The car is that way. But he is seeing photons from that direction, and that's why it's hard for him to see. He sees this glow in that all general direction. Now, you have handouts and text in the book that explains lots more examples of how scattering works in the atmosphere, like the story of how red sunsets work and so on. But let's actually just focus on those examples for right now and answer a few questions before we go on to the next part of the lecture. Question 7. Which of the following is not something that clouds do? A. Clouds reflect shortwave radiation from the sun. B. Clouds emit shortwave radiation. C. Clouds emit long-wave radiation. Or D. Trick question, clouds do all those things. Which of these is something clouds don't do? Alright, make a choice from those 4 options and get a little feedback before we move on to question 8.